Two cars, identical in every way. Same weight, same tires, same transmission ratios, same aerodynamics. The only difference is the engine. Assume neither car is traction limited, and assume each driver shifts to keep the engine in its strongest operating range. Car A makes 200 horsepower and 100 pound-feet of torque. Car B makes 100 horsepower and 200 pound-feet of torque. Car B has twice the torque. By most people's instinct, Car B should win. More torque means more force. More force means faster acceleration. That's the logic. But that logic leaves out the part that matters most. Under those conditions, Car A, the one with half the torque but twice the horsepower, will accelerate harder overall. To understand why, we need to build from the ground up, starting with torque. Forget the engine for a moment. Imagine tightening a bolt with a wrench. When you apply force to the handle, the bolt does not move in a straight line. It rotates. The force is useful because it is applied at a distance from the center of rotation. That distance is called the lever arm. The longer the wrench, the more torque you generate from the same applied force. This is why a long breaker bar can free a bolt that a short wrench cannot. Same force, different lever arm, different torque. Inside an internal combustion engine, the same principle applies. The geometry is just more complex. Combustion pressure pushes the piston down. The piston drives the connecting rod. The connecting rod acts on the crankshaft. Because the crank pin is offset from the shaft's center line, that downward force creates a turning effect. That turning effect is engine torque. So at its core, torque is simply force applied at a distance from an axis of rotation. More cylinder pressure, a longer effective crank throw, or a more favorable crank angle all increase the torque produced at that instant. But torque does not tell you how quickly that force is being applied. And that is the entire problem with using torque alone to judge an engine. Power is the rate at which work is done. Not the amount of work, the rate. If you push a car from point A to point B, you have done a fixed amount of work regardless of how long it takes. But if you do it in half the time, you have used twice the power. Same job, half the time, double the power requirement. Inside the engine, this means torque and rotational speed have to be considered together. An engine producing torque at a slowly spinning crankshaft is doing less work per unit of time than the same engine spinning faster. Power depends on both. In US automotive terms, horsepower equals torque times RPM divided by 5,252. The constant 5,252 comes from the unit conversion between rotational speed, torque, and mechanical horsepower. It is a fixed mathematical result of those unit definitions. What this formula tells you is that two variables determine horsepower: torque and how fast the crankshaft is spinning while that torque is being produced. Change either one and horsepower changes. This is why a diesel truck engine can make enormous torque at low RPM, but relatively modest horsepower. And it is why a high-revving naturally aspirated engine can make strong horsepower from comparatively modest torque figures because it sustains that torque at much higher engine speeds. And here is where the thought experiment from the beginning starts to resolve. Engine torque is not wheel torque. Between the crankshaft and the road surface sits a transmission, a final drive ratio, and a tire with a specific radius. Each of those elements transforms the engine's output before it reaches the contact patch. A transmission multiplies torque through gear ratio. First gear acts like a very long wrench. It increases the torque delivered to the wheels while reducing wheel speed for a given engine speed. Drop to a lower gear and you trade speed for force. The engine does not change. The output at the wheels does. For example, suppose first gear is 4-1 and the final drive is 3-1. Ignore losses for a moment. An engine making 100 pound-feet at the crankshaft would deliver about 1,200 pound-feet to the axle. An engine making 200 pound-feet would deliver about 2,400 pound-feet under the same ratios. Gears can multiply torque, but gears do not create power. They only trade torque against speed. So now return to Car A and Car B. Car A has 200 horsepower and 100 pound-feet of torque. Car B has 100 horsepower and 200 pound-feet of torque. Car B's torque figure looks stronger at the crankshaft. But Car A can add energy to the vehicle at twice the rate. And when acceleration is the question, that matters more than the torque number by itself. This is the key distinction. Acceleration is not about crankshaft torque alone. It is about the force at the tires over time, which depends on torque, RPM, and gearing together. Peak torque tells you where the engine produces its greatest twisting force at a single point. Peak horsepower tells you where the engine is doing work at the highest rate. For acceleration, which requires continuously adding kinetic energy to the vehicle, horsepower is the more complete single number. If horsepower is the more useful figure for acceleration, why does torque dominate so many conversations about performance? Because in a single fixed gear, it does tell you something real. If you are driving in third gear and you pass through the engine's torque peak, that is genuinely the point of maximum push in that gear. The force at the wheels is highest there. The seat of the pants sensation is strongest there, and that feedback is immediate and physical. Human perception responds to that shove, not directly to the rate of work being done over a full acceleration run, but the moment gearing and shifting enter the picture, the situation changes. A well-matched transmission can keep the engine operating near the strongest part of its power band across a wider range of road speeds. The sensation may be less dramatic than a low RPM diesel surge, but the rate at which kinetic energy is being added to the vehicle can still be higher. This is also why two engines with identical peak horsepower can feel completely different. One may produce a broad, flat torque curve from low RPM, responsive, effortless in everyday driving. The other may make most of its power near redline, requiring commitment, demanding the right gear. In a controlled acceleration run with optimized shifting, the one that sustains more usable power across the run will generally be quicker. In traffic, the broad torque engine may feel sharper and easier. Neither is wrong. They are built for different operating philosophies. One more place where this distinction matters is top speed. At high road speed, the vehicle is no longer primarily fighting inertia. It is fighting aerodynamic drag, and drag scales with the square of velocity. The power required to overcome it scales even more aggressively. Doubling road speed does not double the drag power requirement. It roughly cubes it. A strong torque figure at low RPM does not help much at 124 miles per hour. If the engine cannot sustain adequate power at that speed, the gearing has to place the engine in a useful part of its power band. And the power output at that point has to exceed the sum of aerodynamic drag, rolling resistance, and drivetrain losses. Top speed is determined by where the power curve intersects the resistance curve, not by the torque peak. So here's where we return to the beginning. Car A, 200 horsepower, 100 pound-feet of torque. Car B, 100 horsepower, 200 pound-feet of torque. Car B feels stronger on paper. That torque number is more visceral, more concrete. It is easier to imagine 200 pound-feet of twisting force than 200 horsepower of abstract rate of work. But acceleration requires adding kinetic energy to the vehicle continuously. The faster that energy can be added, the faster the car moves. That rate is power. And power is what Car A has more of. So the question to ask, if someone quotes you a torque figure as proof that an engine is fast, is, at what RPM does it make that torque? And how much power does that correspond to? Torque is the twisting force. RPM is how often that force is applied. Horsepower is what you get when you combine both. And gearing decides how all of it reaches the road. The engine moves the car by delivering power, through a transmission, through a final drive to the contact patch, faster than the forces resisting motion can prevent it. That is the complete picture. If you found this explanation helpful, subscribe to Engineering Manual for more breakdowns on how modern engineering systems work.